Hi everyone, it's 2 minutes past the top of the hour, so we'll get going. We have an hour and a half of material to get through. Thanks and welcome to the seminar that we're running today. We've run it twice. It's in theory a PDAC event. We ran it last night in a time zone friendly for our America's colleagues. Today we're running it more in an Asia Pac type time frame. A bit like PDAC, when we ran it last night, it was late, it was dark, we were tired running it live, and it even had a few drinks, so it's a pretty good simulation of running these things at PDAC. But there was one difference though. At midnight last night in Perth, it was 31 degrees outside, plus 31, not minus 31 with the wind chill, which we'd be often coping with in Toronto. Now, just to get into the seminar. So the title of today's seminar is "What's the Real Value of Data and Pulling Decision Points Upstream?" Which we will get into and expand upon during the course of the next short while. I'm Dave, for those who haven't met me, the Chief Geoscientist, and I'll be talking around and some background around the industry's attempts to find, define and mine, and why it's becoming increasingly important to speed up that process and what role data has in enabling that process to be more efficient and for the industry, and just how the industry really needs that at the moment. We're entering very interesting times. Following on, I'll hand over to Charles. So Charles Mcfadyen is our General Manager of Drilling Optimisation. He's going to talk about the importance of drilling smarter meters, in the find and define phase of the work we do across the mining value chain. It's really all about drilling. It's a key way for us to obtain the samples which generate the data. So doing it smarter and more efficiently is a key technology to unlock value more quickly. Following on from Charles, we have Sasha Pontual, who I've known for many, many years. He's our Global Product Manager for Automated Mineralogy. Obviously, Sasha's come to us with the acquisition of Auspec just last year, and we very much just think it's excellent to have Auspec on board. Sasha will be talking around, the ability we have now to generate mineralogical data virtually in real time, and the importance of having that as early in the resource definition phase of a drilling project, especially as early as possible, to mitigate some of the problems we have down the track. Many problems we have when we get through to actual mining phase can be mitigated by having that information early, and that's the whole concept about having data upstream. Don't wait until you have a problem now when you try and bring something in production. Fix the issue upstream, and that's the emphasis of that. And then finally, we have Putra Sadikin over in Melbourne, our geochemist and senior software analyst working in the ioGAS team. Many of you will also know Putra, or have dealt with him over the years with ioGAS. He's also going to talk about the importance of being able to look at that data when you get it, at the time you get it, and make important decisions, again, in real time. So now just to, sorry, I'll just advance this. So I just want to give you some context to think about when the next series of 3 talks come up. Just a macro scan of what's going on in the industry at the moment. What are some of the big headline issues that are going on? And all of you work in industry, so these won't be unfamiliar to you, but I'm going to pull out a few things which have been interesting. So at the moment, the industry is dealing with the desire of governments and large corporations and large financiers to drive a decarbonisation agenda, with some targets being as early as 2035, going out to 2050. I'm just going to talk a little bit about what that means for our industry. It's linked to another thing which we need to bear in mind around resource nationalism. The more important some of these commodities that are relatively scarce at the moment, or the more important commodities that are relatively scarce at the moment become, then the more resource nationalism problems may potentially impact on their supply, but I'll expand on that. And to supply a lot of the metals we need, future-looking metals, as sometimes get called, we're going to require concepts around precision mining. How can we extract these things with the lowest possible footprint, to talk about the decarbonisation angle, but also how can we just get at them and unlock them, period, because the world is going to need them. now some expansion on those themes. So, you know, over the years, we've often spoken about what does IMDEX do and what can it bring to the industry. We never say that we can solve every problem that the industry has or that the world requires that the industry solves. But certainly we have lots of technology which allows us to do things like with our drilling technologies, which Charles will talk about, to test more targets. A fundamental part of the equation or the success in exploration is the ability to get out there and actually test the targets quickly and efficiently. The more you test, the greater your probability of success. Similarly with drilling technologies, decreasing the time to define a resource, but that's not just drilling it out, it's actually getting the data to define the resource properly, to get very high spatial fidelity, comprehensive data to give you optionality around mine designs, for example, which then allows you to design a more efficient mine, and that's around improving mining productivity. We also have some technology going into that realm as well, but that's not so much the emphasis of the talk today, it's more around the top two. So just some forward-looking comments here. This is not our graph. This is a graph created by Glencore. The red box there is a little typo where they've got 507 million tonnes of cobalt. That would be a challenge. It's meant to be kilotons. But just take a bit of a helicopter view of that. They're predicting the requirements of these four metals in particular out to 2050. And just to roll them up a bit, they're saying that we need 4 times, you know, per annum production, 4 times as much nickel and cobalt, and more or less twice as much copper and zinc. That's easy enough to roll off the top of your head or just say it out loud. But actually, the industry is going to have a lot of challenges delivering that into the marketplace if the world needs it to decarbonize and build a whole lot of infrastructure. So not only is it difficult to add supply around some of these things, the supply of many of these metals is influenced by geopolitical problems as well. There are supply chain issues. So if you look at just a selection of metals there in that table, the ones in pink really have quite significant geopolitical influences on their supply chain. So, you know, well documented one, for example, is rare earths. When you look at a table like this, you need to separate mining supply from processing and refining into an industrial product. But some of these, so the rare earths, so China dominates both the production and refining into a useful material. Cobalt, the DRC dominates the supply, the raw supply, the mine supply, but the refined output's dominated by China. Platinum, more so than palladium, if we're looking at future uses of these metals, platinum has some applications perhaps in hydrogen cells. South Africa very much dominates the mining and refining in that world. Lithium, Australia actually dominates the mining supply, but of course it gets processed in China. And graphite, China dominates that. So it's a complex, situation to navigate our way through. Some of the other ones there that aren't highlighted in pink are interesting. So zinc, yes, China does dominate the mining supply, but that will probably reduce over time, and there is plenty of capacity to add, if we can find it, zinc mining supply around the world. Nickel, you know, again, something that the rest of the world can step in and supply. I've just wrote not China there. And in fact, just this week, we saw the story about Indonesia wanting to ramp up the supply of nickel from laterite nickel, notwithstanding the difference in the qualities of nickel needed to supply raw materials for battery production. But an interesting one there I want to highlight is copper, which is not normally lumped in with what people call critical minerals or critical metals. Chile is the dominant global supplier of copper, but Chile was not going through such a great phase in its political life just prior to COVID, and might expect that to come back. And a lot of its large mines are now struggling to supply the copper that they have been as they move underground and they fight for access to water resources and things like that. So there is actually a geopolitical influence on supply of copper into the world as well, which to look at copper, and the reason why I'm emphasizing copper here a bit is people do talk about the other metals quite a lot when they talk about critical metals. Not so much copper, but there's just a couple of little quotes here I want to pull out, which come from things that have been in the media just in the last few weeks, really. So in the next 15 years, we'll consume more copper than we did in the last 100, assuming we can supply it. And the one in the middle bottom there, electric vehicles are very popular in the press at the moment. But if you look at that, if by 2040, and that's not that far away really, 500 million vehicles are converted over to electric vehicles, and that's only a third of the global fleet, right? I'm thinking about that. Just that alone would require 40 million tonnes of new copper to be supplied to do that, which is actually 2 years worth of total supply that we can supply right now. So the question comes about where is all this copper going to come from? This is a slide of Paul Agnew's Rio Tinto, and you will know this, that finding copper resources which are mineable and mineable profitably and big and can supply a lot of copper is not easy. And we've been looking and exploring for copper for 100 years and exploiting it hard for 100 years. So it's not that easy to bring on supply of copper just like that if we're talking about trying to double production from 20 to 40 million tonnes in the context of 15 to 20 years. And this is just another graph to emphasize that point, the timescale. The red bar on the right there, that's the copper price on the right. That timescale of 06 to 20 is the same as the timescale on the left, which gives you the global mine supply. So you can see here that short-term price fluctuations does nothing really to impact global copper production. It's a much longer term thing. You need to have a 10 to 20 year time frame when thinking about global copper production. And one of the worries I have here is that with the vehicle makers going to order their million tonnes of copper in 18 months' time, that the cupboard may well be bare. If you think about trying to supply 20 or 40 double production of copper in the next 20 years, then we'd need to be bringing an Escondida online one a year, every year for the next 20 years, or 2 Kamoas, things like that. So, man, it's a big challenge for the industry. Coupled with the copper mining project pipeline, which is in a pretty dismal state after being underinvested in for the past, say, 8 or 9 years since the last global crunch. So these are just things to think about in the context of what the industry needs and what technologies we need to be able to bring to bear on these problems. But here's another thing just to think about for our industry, and I couldn't resist but put it up here just because of the title. I enjoy showing this to mining engineers, of course, but it gets me a lot of grief. But geologists are gods of mining, says Friedland. Well, I mean, half the world thinks Friedland a genius, half the world thinks he's an idiot. It's a bit like Elon Musk. Maybe he's our industry, it's Elon Musk. But this was actually a very interesting article that he wrote, linking blockchain technology, putting a price on carbon and having that reflected in the price of copper. So the point he's making here is that perhaps in the future, and you don't need to use your imagination that much to think about this, is there won't be a single price of copper in the marketplace. It will be priced on the amount of carbon that's gone into its production. And that's easy to imagine, especially if it's trackable using blockchain type technology. So when Apple rolls up to buy copper, they will pay more for low carbon input copper than not. So it's something that the global industry will be thinking about, and it's something that we should be thinking about as well when we go about exploration processes and bringing these things into production. What is the carbon input into them? And just a diagram here to illustrate the relativity or the sense of this problem. That's Palabora mine over in Africa, but it just shows to scale the amount of copper that was extracted from that giant hole in the ground. And you can see here why we are quite a carbon generating industry, having to move that much rock to get that much copper out. And we need a hell of a lot more copper. So just a bit more about having the right information at the right time and what is the value of that information. So pushing the acquisition of the data upstream and what's the value of doing that. We're doing some work with John Steen and Mike Samus and Andrew Gillies. So John and Andrew over in Vancouver, Mike's over in Toronto, looking to actually calculate what the value of this information is. But part of this is that Andrew Gillies especially has been looking at asset impairments, so reported asset impairments on the TSX, and what was the key causation of the impairments. When he started this work, honestly, I thought most of it would be, well, geopolitical, commodity price related, things like that. But in fact, fully a third of the asset impairments announced were due purely to rock knowledge, not having enough rock knowledge, not having enough upstream data to avoid a problem later on down the track. And the comment along the bottom there from John Steen is that that having the size of these losses and impairments would seem to put a strong case on placing a high value on having the right information at the right time. And that's the theme we are talking about in the next few talks. I'm just trying to. And here's a real world case. So this is some work done by Rick Valenta, just been talking about the desire of the world or the need of the world for a lot more copper. There's a whole lot of projects there or resources which haven't quite made their way into production yet for a whole variety of reasons. And the reasons are low risk to high risk. So the darker grey, the black are the most problematic things categorized among the top there. And you can see here, a lot of these resources are not in production, not due to grade, but due to a whole lot of other things. And this is a classic example of not using upstream thinking. So getting to the end of the process and realizing there's a problem with access to water, tailings management, ore deposit variability, where is the arsenic deported, and not having enough ore body knowledge to at sufficient spatial fidelity to give you optionality around the infrastructure development so that you can come up with a different mine design which has a much lower footprint and perhaps a much lower carbon footprint as well. So it's just a real world example of that sort of problem. So I'm going to finish up now and hand over to Charles very soon, but I just want to leave you with a quote here. Tony O'Neill, technical director at Anglo American, he riffed this off in the middle of a presentation he was giving to CRC all late last year, but it's a good one. And I'll, you can read it, but I'll read it out. But it says we need to get to the point where society views mining is necessary for the well-being of its own existence. And here, but man, what a challenge that is. But I'll put another one, and people scoff at it and say there's no way that's going to happen. Well, Dator, who's a noted futurist, has got a law underneath there that says that any credible idea about the future must at first seem ridiculous. So maybe, perhaps, there is some hope for us. So they were just some things I wanted to plant, some seeds I want to put in your mind, give you some context to think about the talks that are coming up. I'm going to sign off now. I'm going to hand back over to Shu, and Shu will then bring Charles online, and he's going to pick up with the importance of drilling smarter meters. Thanks for listening, everyone.
Thanks, Dave. We now just change presenter to Charles.
Yeah, hi all. Hopefully everyone can see my screen. Yeah, thanks, Dave. I'm going to talk a little bit about the importance of drilling smarter meters. I'm the GM for drilling optimization here at IMDEX. Previous history in the exploration drilling space, and then into mining a little bit later. Let me just get this to work. We're going to talk, I guess often, as Dave touched on, we talk a little bit about the value mining chain. Today, I'm going to really focus around exploration, discovery, and definition. And our ultimate goal here is to test more targets, decrease the time to define that resource, and the ability to drill these smarter meters. And I'll touch on that as I go through this presentation. But we're going to be talking a lot about, a typical diamond sort of coring rig, running an SRU, and then looking at the influence of new technologies and how we can really, in part, optimize this process and really look at, some smarter solutions that help us all in resource definition. I guess this is a little bit, in some ways, obvious, but drilling data is obviously the primary source of information used for major investment and decisions by a resource company. And we see a large part of that starts with drilling. And I guess it's important to understand how we can look at drilling more targets. If I stand back from this and I think about drilling smarter meters, for me, it's really probably 6 things. There could be many more, but I would define it in 6. And today I really want to talk about sort of 4 of those. I think there's a big play here on environment, health and safety, a little bit what Dave touched on, but I'll expand on that. The next one is really for me around cost, performance and data. I think they come together, and I'll probably explain a little bit of logic of how I look at that. I think overarching a little bit like EHS is quality and why we need a quality core sample to make decisions. I think that's essential. And then I'm just going to talk a little bit about new technology and probably, a really interesting space for me personally. But it's also, how do we solve some of these fundamental problems? And I'll give you some examples of some new technology and the way that we've looked at it. So if I start with environment, health and safety, I think, like I sort of touched, this is overarching to any drilling program to ensure that we have zero harm and maximize the efficiency while we're drilling in these remote locations. I think the industry's already seeing significant changes towards automation, which has come out of mining and into that mineral exploration. We're seeing the standards of QA/QC increase globally. Obviously, there's a huge demand and thirst for more efficient programs and drilling more targets. But obviously, we all strive for leaving a smaller footprint, and Dave touched on, the CO2 topic around mining, but I think the environmental impact is very much there, and one of which ways we can do it when we drill is water, which I'll touch on a little example shortly, tied to solids removal units. But really, another industry problem is really around handling drill pipe or handling rods in and out of a hole. And I'll touch a little bit later on new technology of how we can solve that. But also we see a declining skill set in driller experience and competencies globally. So I see this is an important part of being able to drill in that smarter scenario. The scenario, one of the sort of examples I would use here is really around what we call solids removal units, or SRUs. I guess familiar to many, but not everywhere globally is using them. But the significant advantages here, in a lot of ways, it's obvious, but predominantly in diamond drilling, we'll dig sumps in a one way of doing it. We drill sumps and circulate the cuttings between two sort of open cut holes in the ground, or potentially nesting tanks. Reducing that impact on a footprint and the potential to have to rehabilitate that after a drilling program's finished, or as we move off that physical pad or location. We're talking about big savings in water reduction. We're talking about reducing the amount of time spent physically carting water back and forth, as we're able to recirculate a lot more efficiently. And there's some big figures on this slide. It's a little busy, but I think that these values we have seen time and time again as we look at this globally. We talk about reducing the fluid consumption and really optimizing that fluid delivery to a moment in time down at the bottom of the hole where the bit interacts with the rock, and we see significant advantages not only in fluid consumption, the right fluid delivery, but also it has an influence on rate of penetration. So we know that the more solids that we carry, it decreases the performance of drilling. I think for me, the SRU represents a great opportunity for the industry to embrace not only a more sustainable approach to drilling and a smarter approach to drilling, but it's really actually increasing productivity. So I think it's a win-win for all involved. But there's good initiatives out here that we can use to further ourselves in drilling smarter meters. If I get to sort of the next couple of points where I brought them together, cost, performance, and data, I see that these come together. Obviously, we need to balance that equation between cost and performance. But I guess the industry has seen drilling get more expensive, and we're drilling more undercover, we're drilling deeper. We're drilling in a lot more harder formations. But I think, really we fundamentally need to change the way we look at drilling programs to sort of embrace and allow those further technologies to come in. Sometimes that's not about, reducing the cost in certain areas. It's probably allowing those more progressive new technologies to come in to make that step change in performance. And I've got an example where I talk a little bit about one of our technologies, Extractor, and what that means to a more standard drilling program. We've obviously got higher safety standards, labour costs are increasing, greater environmental and cultural restrictions, which I sort of touched on before. But we need this data. We need this data to define that resource. And we need to really look at how do we become more productive. One of the examples I'll just share a little bit here is, this is an example of a site where we had 6 drills, North America, and we looked at our extractor technology and testing that, which allows us to rapidly deploy. I think some or most will be familiar with that, rapid deployment, and we don't have the challenges of having to pull out of a hole to change our drill bit. So we can effectively, each time we pull a tube, we can change the bit. So we're eliminating that manual handling associated with tripping pipe, but we're also increasing really that productive time on bottom. And I'm going to sort of talk a little bit about that. Obviously, we have a great signal of how our technologies work, leveraging our hub and other rock knowledge sensors to really prove up what they do and how they act well. And if we take that 6 rig model where we've got a program that's over 120 days, if we just look at maximizing that time on bottom using a new technology, it's significant the amount of drilled meters we're able to achieve. So we can see, clearly a 25% increase in effective on bottom time, which equates to being able to drill more meters. In saying that, it doesn't always have to be used that way, and I think this is, will suit others, and others will take, probably the increase in drilling more meters, but we're able to use that saving many which ways. On the far right of screen, one of those savings would be that we could physically reduce the amount of drills for a given program and achieve the same 62,000 meters, which was what was targeted. The second scenario, we could keep the 6 rigs and come in that drilling program in a shorter time frame, so significantly saving almost a month of drilling. And that could be given, climatic conditions as well could be an advantage. But the third one is really, utilizing that full capacity, keeping with a 6 rig program, but literally discovering more targets. And there's going to be a lot of resource companies that really want to drill more meters to define that resource quicker. So I think there's many which ways we can look at that ability of using a technology, effectively increasing our performance and drilling smarter and tailoring a program to suit. And I think IMDEX plays a big role in trying to be that bridge to sort of look at this holistically and offer solutions. This slide here is a little bit of a picture of our testing facility in New Zealand, where we test up our drilling technologies. We have 2 drills in which we do our own sort of R&D and field work, and then we go out to effectively end customers to prove up and further validate function and performance. But I guess traditional data handling and management practices lead to delays and costly mistakes. I think Dave touched on that with the work with the team in Canada, but this sort of false negative or missed signals that we see in and around the field can be costly. So for us, it's a balanced approach to not only looking at the new technology, but really having the data and the signal strength that we can really make fact-based decisions on that and look at how that technology works. So you're seeing a big wave in sensor-enabled drilling, measure while drilling, and then other forms of sort of time in motion and stuff that IMDEX is familiar with. This one is really around quality. I think this one is relatively obvious to me and it's overarching, but any type of drilling or new technology we introduce, it has to be of an overarching standard of quality. And that's in diamond drilling, we talk a lot about core recovery and the quality of that core recovery. I think it's incredibly important. That's ultimately why we're drilling the hole, to get the core recovered, and then to look at how we log and sample aspects of that, and then model that resource. So I think that this is where Sasha and Putra will continue that discussion and share a little bit more of the value of that information and data. But I guess it comes back to that find, define, and mine cycle, and doing it really precisely. And that's something that a standard that we at IMDEX really hold as important. So it's not drilling quicker meters; it's really drilling smarter meters with an emphasis on it has to be of a quality product that we effectively recover out of the ground. And allowing that, still to test more targets at an early stage. Probably where I'm a little bit more passionate is about, the influence of new technology. You'll see a picture in the top left here of MagHammer, one of our new technologies. And then on the right, a Boss unit where we can inject fluid into a given point in the hole. But I think that really all major advancements in drilling will really come from the use of new technologies to really increase drilling efficiencies. And I think that's an exciting time. I see that when I started exploration drilling some 20 years ago, I haven't seen a lot of change. I've seen change come through mining. And I think that, from my perspective, the technology is ready. I think that the drilling rig and the modern drill of today is ready to handle these new technologies. I think as drilling companies, as resource companies, I think we're well in tune of how to deal with it, how to handle, looking at that data and making informed decisions. I think automation is a step that's ready and ready to be deployed in various aspects. Automation is a very varied topic of what that is by definition, but I think more autonomous solutions are going to come and will be around in front of us, which will enable, obviously, in part, a more productive solution and definitely a safer solution. I think fluid technology is something that obviously we've been in and around for a long period of time. We see that as enabling a lot more efficiencies, and that's in and around that bit-rock interaction, and also the ability to lift and remove those cuttings, so we can maximize quality of core, and also some of the challenges that happen at drilling deeper, right? Obviously increasing torque and other physical challenges that appear. And I think that to sort of touch on a little bit data again, I think that measure while drilling data is and software is incredibly important to drive what are we seeing and how do we become more efficient, and sort of connecting all of us together to make those sort of more fact-based decisions on increasing efficiency and also productivity. The one example I have here is MagHammer. So like I showed you a little picture of MagHammer. MagHammer for us at IMDEX is actually really two products. One is a conventional flushing system, so we're talking about the cuttings coming up the outside of the bottom hole assembly, and sort of the cuttings would be coming out at the top of the collar, not really collected. You could sort of sample in and around the collar. But the other solution for us is a full face sampling solution, so very similar to an RC hammer. This is just magnetically controlled and fluid operated, allowing us to compare ourselves towards an RC drill. So for those very familiar with RC drilling, it's incredibly productive. It gives a high quality chip sample coming in and out of through the internal rod string, but it's incredibly heavy on CO2 and the input of power, and that power comes in the form of compressed air to make everything work. So often you've got quite a large size drill to turn big rods. You've got a compressor on that drill to obviously distribute the air, and then given depth, you'll be running a booster and an auxiliary to further increase the efficiency at depth. So as you add more pipe, you lose air, not incredibly efficient, but use a lot of fuels to power that assembly. So what we're able to do with MagHammer and our RC version of MagHammer is we're able to use a traditional diamond coring rig with an SRU, of course, to optimize fluid and fluid cuttings to get those samples in and out of the hole. But we're able to maintain a really high rate of penetration, especially compared to normal diamond drilling, and really have a more environmental footprint. We're not generating the dust because we're suppressing that with water. We're circulating and recycling that water. We're not drilling sumps, and we're able to drill at significant depths here, where we're not as limited by the factors of compressed air. So it allows us to sort of options to rapidly get to depth of a particular target or intercept, and then the ability to even change over and look at other forms of perhaps coring the tail of that hole, given a reef or some interesting intersection. So for me, this is a really exciting technology that really changes the equation in exploration drilling, and I'm really excited to sort of start talking more about this and explaining how we look at technologies like MagHammer, which we haven't really seen come into the industry until now. So I'm going to pass the baton here. I think we've got a panel at the end where we'll happily take any questions. For me, thanks all. Really great to join, even though it be virtually. I'm really passionate about this industry and wanting to see a change, and I really see IMDEX being a big part of that, and look forward to maybe taking some of those discussions furthermore to see how you look at it. Is there something else? And there's many more to talk, but hopefully I gave a little sneak peek at some of how we look at the influence of drilling smarter meters. Shu, I might pass back to you.
Yes, thanks, Charles. Thanks for the presentation. So next we have the presenter is Sasha.
Thanks, Charles. So my talk is about digital mineralogy and why this is important for exploration and mining. So to date, as we're aware in our industry, that there are millions of mining investments that are based on knowledge of a very small amount of a deposit, maybe 1% of 1% of the deposit. And traditional mineral analysis methods that have been carried out to date tend to be quite expensive, and also provide quite a low resolution understanding of the deposit in terms of the ore body and the associated alteration. And in the end, really, a lot of the problems that we have in mining are related back to the mineral data and alteration minerals in the deposit. And often these are recognized much too late. So how can we actually do this better? So what we need really is better resolution mineralogy data to be able to make better decisions. So for example, we might have two deposits here. And when we're actually looking at them in low resolution, they look fairly similar. But as it happens, you know, we've got our Tesla on the left here, which is our nice economic deposit with really manageable mining and processing challenges and rewarding returns, so economically viable. And we might have our Corolla on this side, which may be much more challenging. And so we've got a lot of low returns for a lot of effort because of a lot of issues with processing and slope stability and so on. So mineralogy is a key component really to actually differentiate between these two different styles of deposits. And the earlier that we have this information, the better. So how can we do it better? We really need to know our rocks in detail. As we all know, geology is complex and not always predictable. And it's really important to build that mineral knowledge throughout the project lifetime, from the discovery phase all the way through to mining. And the low density sampling, which is often done these days in mining, is not sufficient to actually give us the type of resolution that we need and to save us from unwanted surprises during the mining lifetime. And these can all have really adverse effects on the economics of a deposit. And this is mostly because the sampling in mines, and once we get to the mining stage, is not adequate. You've got sampling that's selected using geostatistical methods, and then extrapolation of those mineral domains across the deposit in a very low resolution representation. I just want to go through the mining life cycle really, or the exploration mining life cycle as to where mineralogy sits. So at the exploration stage, so why is mineralogy important at this stage? At this point, we're trying to define, you know, do we have something viable, and how can we understand what we might have as a discovery here? And usually the samples that people are looking at are soils samples from shallow drilling, perhaps RC or RAB drilling, and maybe a few diamond drilling in those more exciting discoveries or exciting projects. And basically what we're looking at this point really is assessing mineralogy for understanding the alteration within that particular region, that project area, and maybe using mineralogy to vector towards higher temperature or more mineralized parts of the system, and then being able to make decisions about where to drill next and have a better understanding of where the system is going beyond that. So as an example here, in a soil mapping exercise, for example, you might be doing a geochemical soil survey and actually seeing some interesting geochemical anomalies in a project area, identified by whether it's the gold or whether the sort of antimony, moly, and bismuth type signatures. We can see we have some elevated values in this particular project in the soil survey in the geochemistry. And to understand this a little bit better, to actually bring in the mineral information, then allows us then to maybe make more sense about what we're seeing in the geochemistry, and look at perhaps the porphyrite distribution here, and then the alunite distribution in this particular project, and alunite types. In this particular region, we have an epithermal system in the western part of the system, and then over to the east, there's a potential for a buried porphyry system that is being shown by a porphyrite signature and alunite and different types of alunite over that particular part of this project area. So as the project evolves, we're actually trying to, we've made a discovery, we're trying to define it a little bit more as to how economic it is. And at this point, we're doing much more diamond drilling because we're trying to be a lot more specific about the information that we're acquiring. And the mineralogy at this point is important for defining alteration models even more, to actually look at the extent of the deposit, and again to make the economic decisions about, you know, is this a good deposit to be mined? So aside from obviously the mineralization side of things, the alteration mineralogy should play a key part at this point, because this is where we can start to define the potential geometallurgy problems that we might encounter further downstream. So an example here is the Alpala deposit, which was discovered some years ago. But over a number of years, they've been analyzing the mineralogy of samples that have been analyzed also for geochemistry. So these are samples that were sent into a geochem lab. They were crushed. There was a split made part of the sample was analysed for geochemistry, and the remaining part of the sample was analysed for the TerraSpec for the mineralogy, for the alteration mineralogy. And so combining that information for the geochemistry and the mineralogy information, we had an evolving and detailed alteration model building up over time as they evaluated this deposit through that period. So we've actually then defined that we have a deposit. We're looking at mining it now. And at this point, what we're doing then is collecting samples in blast holes or more diamond drilling, maybe underground drilling. And at this point, then we're refining what we know about the deposit. So this the mineralogy then is important to perhaps refine those alteration models a bit more, but also very key for actually making decisions about what we're actually going to do with the material as we start to extract it. So to start to build those block models of the alteration minerals and the potentially deleterious minerals is really important at this stage, and to understand these before any of this material starts to go into the processing plant. And the kinds of things that we can start to perhaps start to model at this stage is to look at certain characteristics of the minerals. So whether it's the presence or absence or the relative amounts of particular problem minerals, or we could also evaluate certain characteristics. So this is an example of the Kışladağ gold mine in Turkey. In this mine, we were able to analyze the variations in white mica crystallinity in their phyllic alteration. And this also correlated really quite nicely with some of the geotechnical analysis that they were doing, and also correlated spatially with zones of poor rock quality and friable rocks. So again, all this information is really useful when you're starting to plan the mine and the shape and slope stability of the pit. So the final stage when you're actually processing the material is going into plant feed into the plant. At this point, the mineralogy should only really be used for monitoring what's going in, just to make sure that there's not any deleterious material or intervals that have actually been missed. But actually, you should not be feeding this material into the plant at this stage, obviously, because we should have actually identified this much sooner. So this is just some examples about how we can use mineralogy throughout the exploration and mining life cycle. So what sort of technology should we use to do this? So why should we use the maybe handheld near-infrared spectrometers? This technology has been around for about 30 years now, and quite a few major mining companies have been using the technology. The main reason being that you can very easily extract alteration mineral data from the data collected by the spectrometers. And they're very portable and they're easy to use in different environments. So you can use them in the field or in the core shed, or even set up in the office. And they collect samples within a matter of 10 or 20 seconds. So it's very quick to actually collect large project-wide data sets. So it can be a very cost-effective way of acquiring mineral information. And when you combine the infrared spectral survey with a geochemical survey and integrate these data, you can really start to, they're very complementary data sets to start to get a more comprehensive understanding of your deposit. So why is the infrared useful? Basically, this technology allows you to analyze most of the alteration minerals that we see in the majority of hydrothermal alteration deposits. We've got a whole range of different clay minerals can be identified, minerals that are quite difficult to identify using other techniques. Obviously, some of these actually mark problem minerals that can cause issues further down the track. And we can also analyze variations in mineral chemistry and mineral crystallinity as well. So that allows you then to use that information for understanding the alteration system and the history of the alteration system much better. And using this data, you can then build quite detailed alteration models, which can help in exploration to actually vector towards where the mineralization is occurring and extend the mineralization, and also allow you to understand the alteration models as you develop the project further. And that information can then go into your geotechnical surveys and geometallurgical surveys as well. With this particular technology, and there's a lot of different solutions of what different types of samples you can use. What we found to be the best is for the handheld spectrometers is to actually use the crushed material. So the ideal sample really would be the material that's been crushed in a crusher. For example, if you're in the field, to use a reflex crusher and create a fine crush of 1 or 2 mil size particles. And this allows you then to have a sample that is homogenized and a bulk sample of that particular sample. And then the remaining material can then be milled and actually made the pucks for the XRF analysis as well, to be complementary with the infrared mineralogy. Alternatively, you could also use the reject crushed material from the geochemistry lab preparation process as well, so to take a split of that material. The other one thing that's key, though, obviously, is to actually be able to monitor the quality control of the spectra that you're collecting. And this is something that we're introducing more and more to companies who work with these data. Historically, this has not been a really good thing. People have ignored quality control. And so we introduced in our Osiris desktop software, we've got a QA/QC feature in there that allows users to be able to monitor their infrared spectra for serious issues such as noise or wetness in the sample and other potentially spectrometer problems. So effectively, what we can do then with this technology is go from our core tray or directly on the core surface, or maybe the crushed materials I was saying, and then collect thousands of spectra that might have corresponding geochemical data with them, and then take these data to start to build our alteration models. So, and what we do, we as well as interpreting the mineral spectra that are the mineral presence in the spectra, we can also look at the details of the spectra, such as variations in wavelengths or depths and intensities of characteristic absorption features in the infrared spectra, and then be able to say something in a little bit more detail about some minerals. So what I have here is an example of some white mica spectra, and looking at the diagnostic white mica absorption, we can take the wavelength of that minimum, and we can extract that as a numerical value, and then visualize that either as a histogram here, or we can start to look at the 3D distribution of those different white micas. So this particular project has 2 white mica phases, a paraganitic white mica and a muscovite paragonite phase, which are quite distinct. And when we plot them spatially, we can see that they create 2 different envelopes of white mica alteration in this particular project. And it's a paragonite that is occurring more proximal to the mineralization in this particular example. And as well as good quality spectra, the other important aspect of this technology is to get really accurate interpretation of the minerals that are present in the spectrum. So using the handheld spectrometer, we are often collecting mixed spectral data. And so it's really important to have a method that interprets those spectra accurately. So we've developed Osiris, which is a technique for a machine learning method for interpreting spectral data. So what I'm trying to represent here is how Osiris was developed. So basically the input data that's gone into the training for the Osiris mineral models are sets of spectra from real world geological projects. So they are not museum pure mineral spectra. These are actually real world mixed spectra from a range of different spectrometers and including a range of artifact type features which might not be related to the mineralogy. So these are actually spectra that are real world, so they're the kind of have all the issues and problems that you're likely to encounter when you're using these types of spectrometers in the field as well. So what it means is that the Osiris interpretation system is really robust across a whole range of geologies and a whole range of different measurement conditions. And so we have currently in the system have gone in over 2 million real-world spectra into the training that have been accumulated over the last 5 to 7 years. And each one of those spectra has been interpreted by a human spectral expert. And so they've been interpreted at the expert level. So as if a spectral expert sat down and interpreted each one of those spectra individually. And that information was then put into the training, and out of that we got the Sirius mineral models. And so the interpretation from Sirius is now, it's achieving human expert level accuracy. And obviously it's incredibly fast. So what we're producing out of Sirius is a result that represents up to 6 minerals in the shortwave infrared part of the spectrum and 2 minerals in the VNIR. And so we can plot out the variations in the mineral content of the spectra. So this is an example from the project in Indonesia, from Bali, and basically what we've got here is the strip logs of each drill hole that was analyzed, and each spectrum that was measured is represented by a single line in this in the strip log, and the width of the colors in the line represent how much of that mineral is present in the spectrum, and this is also output by Sirius. So you can very quickly map the variations and the changes in different intervals as you go down hole. And you can then take those results to ioGAS and start to look at the Sirius results alongside your geochemistry and bring in that digital mineralogy into the your geochemical analysis, and so integrate the data together. And this is when you start to get really the power of these results really become apparent. And in ioGAS we have a set of diagrams which allows you to do more in-depth analysis of certain mineral groups, such as the white mica or the chlorites or alunite minerals. And I think Putra is going to talk a little bit more about this later. And finally, the end objective really is to combine this information along with other geotechnical and geological data. So none of our data sets actually completely standalone. Their strength really is that integration between the spectral mineralogy, the geochemistry, and then any geophysical data. And you start to build up these detailed logs, which then the geologist at the core can actually then use this information and start to make much more comprehensive logs of each drill hole. And that data integration is very powerful. So what does all this mean? So hopefully I've given you an idea of how important it is for us to know our rocks, and that mineralogy is a very key component of this. And also the handheld spectrometers, these are still the fastest and most cost-effective way of collecting project-wide mineralogy. The interpretation of the infrared data using Sirius does allow you to get a much more comprehensive understanding of the mineralogy of each of your infrared spectra. And you can then use these data effectively in exploration and mining. In earlier analyses using other methods, the interpretation was often incomplete, so you weren't able to do as comprehensive a study as we can now with the Sirius results. And so digital mineralogy data can now be a really important part, an important component of the geoscience data ecosystem. And it provides essential information for mine planning. And then, of course, as I mentioned earlier in my talk, that it's really important to do this at the early on as possible, at the resource definition stage, but not at the processing plant. So, and this is where it really sits into the data ecosystem, where we can actually have that mineral information going through all the way from the exploration stage and through to mining. Thank you very much. And I think now it's Putra's turn for his talk. Thanks, Charles.
Thank you, Sasha. Now we have the next presenter who will be presenting is Putra. I'll just switch to Putra.
Hi everyone. I'm just gonna show my screen first. Thanks for that, Sasha. So I'll just bring you through an overview of ioGAS as part of this presentation. So just a bit about myself. So my name is Putra, and I work on the ioGAS product management team. So I have been with IMDEX since we acquired ioGlobal back in 2011. So I started off doing a bit of geochem consulting and carried on to working on the product development team in ioGAS. And what I do now these days is I look after customer support and look after research and development, and sort of being that bridge between our developers and our software customers. So let's take you through what I'm going to be presenting to you today. And so we'll start off with just with a bit of introduction to what ioGAS is and how it really sits in the IMDEX ecosystem of solutions, and sort of what we can highlight out of the features that we have in ioGAS, and sort of how it sits in respect to the other products that IMDEX have. And then we'll just touch on a bit more about the Osiris integration that we have with ioGAS, and sort of how you can use data that we collect from all the other IMDEX suite of solutions and use that to get better value out of your geoscience data. And lastly, I'll wrap up sort of this talk just by bringing it all together by emphasizing the role of ioGAS in delivering real-time rock knowledge to you as users of data from IMDEX as a whole. So what is ioGAS? So some of you who have used ioGAS before knows it as a geochem data analysis software, but over the years it has evolved to quite a fair bit of an evolution. So we started off in 2007, 2008, and we've celebrated our 10-year anniversary with the release of ioGAS version 7 back in 2018, and we have evolved quite a fair bit from its origins as a geochemistry data analysis software. So what it is now, it's actually a complex data interrogation workflow engine that's available to technical experts in the industry, and that includes exploration geos, mine geos, basically anyone who looks at geoscience data. So it's the way that we provide our solutions in ioGAS is it enables technical experts such as geologists to make decisions in a data-rich environment. So in general, geologists are time poor and they have to make quick decisions in a really fast-paced environment. And in recent years, we see another aspect of this is the deluge of data that a typical geoscientist would see in the way that they're working with their data. So what we allow our users to do in ioGAS is to empower them. So we empower technical specialists such as geologists to get insight from their geoscientific data more efficiently. So, and we allow them to sort of do this in real time, closer to the upstream, closer to the point of data collection. And the way that we integrate our solution with IMDEX as a whole is it enables real-time rock knowledge from this data-rich environment of the IMDEX ecosystem. So ultimately, what we want to do is we want these technical experts to be able to extract information from their data in a really accessible manner. So we want geologists who know their data inside and out to use the workflow that we provide in ioGAS to get better insight of their data and to understand what their data is telling them. And we make this process extremely efficient. So this is what we call empowering them to become citizen data scientists. So with being separate from the description of a data scientist, this enables a typical geoscientist who don't have any background in this sort of workflow to be able to apply a data science perspective on looking at their geoscience data. So in the next few minutes, I'll just run through quickly of what ioGAS is. So if if you haven't heard of ioGAS before. So I touched on a bit of this earlier on. It was designed as a geochem data analysis software. And the reason why it was developed like this because it was built as a solution that's specialized to look at your geochemistry data, but in a geoscientific context. So we have a unique approach to exploration data analysis, so EDA and data science tools, but we approach this from a geoscientific perspective. So ioGAS knows basically that you're looking at data that's in geochemical format. So it's not just a table of numbers. And what we have in ioGAS is a library of provided resources that allows you to look at your geochem data in context of your geology. So again, touching on the point of empowering technical experts in the field of geology to really apply their expertise in their background and empowering them to make data-driven decisions much better with the help of ioGAS as a context-driven data analysis tool. And to help with geologists' normal workflow, we have a built-in integration with other leading geoscience and GIS software programs. So some of you would have used the Leapfrog Geo LifeLink before, just linking with geoscience 3D modeling packages such as that. And recently, we've also added a LifeLink with QGIS. So stay tuned on that space because we're getting a new version of that QGIS LifeLink ready in the next little while. So the LifeLink, as it stands, allows you to look at data from ioGAS and enables you to look at that interpretation from ioGAS in your QGIS environment. And the next iteration of that will enable data to be looked at in both directions. So that's where we stand. So those are our partners in partnering up with data interpretation with other leading packages out there. So what we envision for ioGAS is to make it a link between data that we collect from our IMDEX tools and to enable our users to add more value into the data that they've collected in our system. So a bit more on ioGAS. So this is where we started off, right? So ioGAS as a geochemistry tool, so it enables most importantly exploration target generation via context-driven EDA. So that's what we touched on earlier. So the use of our graphs and plots in ioGAS in context of looking at it as a geoscience data set allows you to easily identify anomalies in respect to what is actually count as an anomaly, and also enables you to classify your rocks better and knowing the context of it. And as Sasha mentioned earlier, a combination of the use of geochem data and interpreted spectral in the form of digital mineralogy allows you to really narrow down on alteration zoning and getting the variables that contributes the most to the variation that you're interested in. And that leads to a better way of domaining your geomet parameters from the upstream. So you allow yourself to get a better handle of these parameters closer to the point of data collection, which will enable you to improve your processing costs or recovery rate further down the stream. So ultimately, what this allows us to do is a combination of all these different data types and all our interpretation techniques that we provide in ioGAS is a way to bridge geochemical data interpretation and interpretation of other geoscience data types in a holistic integrated solution. So ioGAS, as it stands, it's not just a tool to collect petrophysical, not to be used on just geochem data, but it's also used to look at petrophysical and structural data as well, and especially in relation to the data we collected as part of the IMDEX suite of solutions and how it stands with the rest of the company is that we collect data from, for example, the IQ logger and from the Easy Gamma. So that allows us to plot our geochemistry data with petrophysical and structural data. So the example that I have on the screen there says wavelet tessellation, and I'll talk about this a bit more later on, is a way of automatically defining boundaries using your downhole gamma data And then on the right is the stereo net. So we collect data from the IQ logger and we plot it up on our stereo net. And that allows you, if you collect your structural data and say your XRF data within the same interval, that allows you to do sort of a downhole geochemical interpretation of your structural features. And I'll touch on this a bit more, but basically what you can do is you can measure the structural orientation of your bedding, and then you collect XRF data based on that particular interval of that bedding, and you basically have a control of how your geochemical patterns, if they're structurally controlled or not. And that's really the power of ioGAS, because we allow all of that to be conducted in a singular workflow within a single session, as it stands. And the most basic feature of ioGAS really is the way that we handle geochemical data. So some of our users are familiar with this, but what we do best in ioGAS is knowing that you're bringing in geochem data, and as with all geochemistry data from the lab, especially, you will encounter problems such as below detection limit and any missing values information, especially if you're looking at historical data. So what we have are tools such as Data Doctor and missing data analysis tools in ioGAS that allows you to clean up your data and to allow you to do other things such as plotting your geochemical data on classification plots, or plotting advanced multivariate statistics, which requires your data to, for example, not be negative or have a less than sign. So it allows you to do it all after you bring your data in, and not doing it in databases or Excel or whatever data format you have before you bring it into ioGAS. And with that in mind, we're pretty flexible in the way that we bring in data. So we can bring in data not just from tables of data, but we can connect to databases. And most importantly, we have this link with the IMDEX Hub IQ cloud-based solution of data. So that's a single source of truth that's secure and it's up in the cloud, and you can access that data from anywhere in the world. And there's only a single version of it out there. So you're pretty secure in what you can bring in data from all of our instruments, and you bring them into ioGAS, and you use that for interpretation. So this is just a quick example of some of the plots that we have in ioGAS. So this is a rather simple example, but this is a combination of our dynamic display in ioGAS. And by dynamic display, it means if you change the color, shape, and size of a data point in ioGAS, it's reflected in every other open plots. While that may sound simple on its own, but once you start actually using it as part of your exploratory data analysis, the value of it means you can quickly identify outliers and patterns in your data, and you can use a combination of different plots to generate outputs highlighting patterns and anomalies much quicker than you would in any other packages out there. So the example that I have on the screen there is just a really simple highlight of anomaly in your gold probability plot, and you can see how that relates to a scatter plot of zinc versus lead, and how it relates to a distribution of our pathfinder elements in that parallel coordinate plot that you see in the bottom. And you can use the result of this in an exported file that you can export out to GIS packages, right? So that allows you to get a better handle of your anomalies much quicker than you would in a typical package that you would use to interrogate your numeric data. And most importantly, you're looking at this in the context of looking at your numeric data in the sense that you're looking at geochemistry data, not just numbers. While ioGAS is not really a 3D modeling package or a GIS package in that, but we do have a couple of unique things. So we can plot our data as interpolated map grid. So that's really good for viewing sort of stream sediment samples and that sort of thing. And we can also plot your data in 3D attribute maps. So this just allows you to look at your drill hole data in 3D space, just to see a spatial continuity of patterns that you would identify from that slide I showed you before. And bringing it all back into what we do best is we bring the context of geochemistry resources into ioGAS. So we are looking at geoscientific data in the context that you're looking at geoscience data. So we're bringing in geochem assay data into ioGAS, and we can plot this up in classification diagrams. And basically what that allows you to do is you can use the diagram on the left, a Janssen cation plot, to classify lithologies based on major elements. So this is particularly good if you're looking at unaltered rocks. And the plot in the middle, just a standard molar ratio diagram that you would use to quantify and identify alteration phases. And of course, if your data consists of not just geochem, but if it consists of digital mineralogy data from OSPEC Osiris as well, that basically allows you to, really put them all into one single database, and that allows you to really narrow down on the sort of alteration that you see in your deposit, not just from your geochem, but from other sources as well. And what we also have in ioGAS are composition nodes. So some of you might have used this already if you're an ioGAS user, but you basically can plot composition nodes, so composition points from a database of known rock composition. So for example, the ones I have plotted up here are from, some of it is from the OSNACA database, from the one that Carl Brohart has kindly given to us as a database that we put in ioGAS. So that allows you to compare your rocks against a known composition in that database. So that basically allows you to see if your exploration program is in the ballpark of something that resembles mineralization. So ultimately, what it allows you to do is to put a bit of context in your geochemistry data analytics workflow. And this is just a continuation of the previous slide of dynamic statistics. And while this may seem simple, but the way that we operate in ioGAS is, if you turn the visibility or colors or anything visual in ioGAS, if you change anything visual in ioGAS, it's reflected in every other plot. And it also changes the way that certain statistics, such as regression analysis, are displayed within the plots. And that also allows you to get a sort of a dynamic way of interpreting your statistics of your data, because you're only looking at data that's visible. That means basically what you can do is you can find outliers or a cluster of data points that you find interesting, and you find the statistics that relate to particularly just that cluster. And that leads me to my next point, right? It's automation methods in ioGAS, and this is what we call the analysis sort of tools of ioGAS. And so I would like to divide this into two parts. So first is unsupervised analysis, and then supervised analysis. So unsupervised analysis requires no prior knowledge of your data. So you don't know about any geological logging of your data. So you don't have any labels on them. And so some of these tools like principal components analysis and TSNE, they're really dimension reduction techniques for complex multivariable data sets, and it enables clustering applications, including pattern recognition of your geochem data. So an example of this, with the principal component analysis, you use this technique to find the first few principal components that summarizes most of the variation within the geochem data that you have, and that allows you to use this multidimensional reduction technique to find the variables that explains most of the variation within your data. And you can use this as a basis for manual clustering, or you can use tools like k-means clustering to find the clusters better, and sort of use that as a starting point to cluster your data or find patterns within your data. So use that as a starting point. So it doesn't replace a typical geologist workflow. So we do encourage users to use this with their own caution. So a typical geologist would use this to find a multidimensional reduction on their data and use that as a starting point to identify patterns and trends within their data set. So, and the best thing about having these tools in ioGAS is that you don't need to know any programming to do these functions in GAS, but you will need to have, a fairly good understanding of your data and what these methods are actually doing to your data. And so therefore, transformation of your data, applying logarithmic transformation before you run these tools is an essential thing. So you need to know your data distribution and their population before attempting to use these tools. But because it's so easy to use in ioGAS, that means you're more than welcome to try it out and see what it does to your data. and if it doesn't do what you expect it to, and that means your data is probably not clean enough to do this sort of analysis. But if your data is in a good shape, then you can find some interesting patterns out of them and use these tools as a starting point for more advanced analysis in ioGAS. So the one on the left here, it's a t-stochastic neighbor embedding. So that's a really long mouthful description of TSNE, but it's a nonlinear dimension reduction technique that again can assist in pattern recognition and clustering. So it can be used as a starting point for finding patterns in your data. And the one on the right is an example of self-organizing map within ioGAS. So again, it's a dimension reduction technique, and what's good about this is that it preserves the topology of the original data, and it groups similar features together, which preserve the relationships within the input variables. And the best thing about it is that you can apply it to other data sets with similar input elements. So the use of these tools, if you know what they do and if you're familiar with the way that they work, is it gives more value out of looking at your geochem data. So there's obviously a certain value in some workflows, such as manual interpretation of outliers and patterns in your data. So you can use things like Scott Haley's workflow of using scatter plots and things like that. And they're really quite useful for finding anomalies and patterns and processes that you can infer from your data. But the use of some of these tools also allows you to sort of approach the data from another way, so from a numerical statistic sort of point of view. And you use that as a starting point to apply your technical expertise. So allowing you more time to look at your data as a geoscientist. So you use this number crunching technique as a starting point, especially useful when you're looking at a rather large data set. And a multidimensional reduction technique such as these can be used to sort of reduce the time it takes for you to work on your data, knowing the context of it as a geoscientist much better and quicker earlier on. So if you know your a priori data, so if you know your log geology before you run it through ioGAS, we have tools such as discriminant projection analysis and classification and regression trees that really allows you to sort of define what sort of splits this categorization a bit better. So an example of this is the use of our classification trees that allows you to determine the most important decision breakpoints that can split the data on known groupings. And the use of things like DPA, discriminant projection analysis, and auto domain diagram allows you to sort of define what sort of parameters were most useful in splitting your data based on known a priori groupings that exist within your data. So let's sort of wrap this up with a few minutes of the way that we integrate data that we process in ioGAS and see how we integrate that with the rest of the IMDEX ecosystem. So as a whole, ioGAS is linked with the IMDEX Hub IQ platform. And by that, I mean, you can bring in data from IMDEX Hub IQ from anywhere in the world, and they can securely import validated field data anytime, anywhere in the world, as long as you have internet connection. And because most of our tools export data into IMDEX Hub IQ, that means you can bring in data from a variety of IMDEX tools back into ioGAS. So out of IMDEX Hub IQ, what I will talk about today for the rest of the session is just our integration with EasyGamma, IQ Logger, XRF, and Osiris Desktop. So I'll start off with the way we integrate with data from our EasyGamma, so drill operable geophysics. So GAS users can import EasyGamma data from IMDEX Hub IQ, and bringing in gamma data into ioGAS, you can use the wavelet tessellation tool. So that's the screenshot in the middle. So you can use this tool to automatically define boundaries that may exist within your downhole gamma. So with downhole gamma, you have really tight spacing, so a really dense data within a particular drill hole, and you can use this to define boundaries as identified by the wavelet tessellation tool. And you can use that as a starting point for defining lithological boundaries. And you use that as a starting point to see if your automated boundary definition sort of matches with what you log physically. And And another tool that we have that uses downhole gamma data is Recurrence Plot. So that's just the one you see on the right-hand side. So the Recurrence Plot basically allows you to do the same things, that automatic classification of boundaries within a densely spaced downhole gamma data. But you can also use the wavelet tessellation tool on geochem data. So I've had success using the wavelet tessellation tool with a combination of other petrophysical data, just combining them together, or you can also use it on a combination of downhole geochemistry. So if your data spacing is dense enough, you can use, say, a principal components analysis result of your pathfinder elements for a particular exploration. So use a principal component of that, the result of that, as an input to use in your wavelet tessellation tool. So that allows you to pick the boundaries as you would see from the signal of that particular combination of elements, or in this case, in your downhole gamma data. And of course, if you have a data set that consists of more than just downhole petrophysical data, so if you have a data set that has correlated intervals with other data types as well, of course, you can combine this with your geochem data and downhole geophysics. And that's really the strength of ioGAS, because you can look at all of this within a single sort of workflow, within a single session. And the next thing I want to talk about is structural geology. So structural geology means that's the data that you collect from your IQ logger. So from our IQ logger device, you can collect data in the form of dip and dip direction or alpha beta readings. And then once you collect that data into and push that into Hub, you can bring that into ioGAS and you can plot them up in our stereo net and in our rose plot, as you can see in that screenshot as well. So this is all QA/QC on the point of collection, which is the strength of it. And obviously, it's all been uploaded to IMDEX Hub IQ, which means there's a certain due diligence there that has been done on the quality of the data. And you can bring that in and from anywhere in the world. And if your geochem data is in the same interval as your IQ logger reading, that allows you to do geochemical interpretation on your structural readings. So if you have, the example that I mentioned earlier, so if you're looking at structural orientation of a particular structural feature, such as a bedding, and then you can see if a bedding consists of a particular feature that you're interested in, and then you take portable XRF analysis on that particular feature, you'll be able to combine that interpretation into a geochemical. You can see if your structural feature has any geochemical implication as well, because you're plotting them all in the same stereo net. So the example of that stereo net that I have in the middle actually has geochem data that's collected for veins. So gold assay from the vein data, and you basically plot that in conjunction with your structural features, and then you can basically see that the higher grade gold is concentrated within a particular sort of structural cluster, and you can use this to infer if a certain structural pattern can be used to predict mineralization or any other geochemical anomalies that you may find in your data. And I touched on XRF for a bit just then, and the way that we integrate with the infill geoanalysis solution is the way that we get really high quality portable XRF data. So that's data that's been fed to the crusher, press and mill and press, and then we apply PXRF reading on this box, and then we bring that data into IMDEX Hub IQ or to the XRF Connect. But basically, we can get portable XRF data and bring that into ioGAS and use that to get interpretation done pretty much on the fly. So you collect your PXRF data, push them to Hub, bring them to ioGAS, and you can say plot a plot of titanium, zirconium, and chromium, and you can really use that to define your mafic lithological boundaries, as an example. So that's an actual user case that some of our users have done before. So they have done, just collected data just from those three elements, and they can use that to sort of define lithological boundaries just by using portable XRF data. So really high quality portable XRF data, you plot them up in ioGAS. So we have a really robust importer tool for XRF data into ioGAS, and that allows you to bring data from our reflex Fanta machines, or from other XRF devices. And we have a detection limit replacement tool, and then you can bring them into IGAS and do your geochem interpretation that way. And really, the power of having all different data types that you can bring into IGAS, really the power of that is you can import data from different sources, so from XRF data or from ioGAS or EasyGamma. Yep.
Yeah, sorry, Putra, we just lost you for a couple of seconds.
Oh, that's all right.
Sorry.
So I just I don't think you missed much back then, but what I was saying is you can import data from different sources. So again, from XRF, ioGAS, EasyGamma, and you bring them into a single workspace. And again, the Osiris integration with ioGAS allows you to import digital mineralogy from the Osiris desktop, and you can push them on into ioGAS, and you can use that to plot it on classification templates that you can see here. So you can basically use this in conjunction with your geochemistry data to define, first of all, alteration boundaries. You can define that better, so to define your mine size and your operation, and to vector into mineralization and sort of scoping out the size of your deposit. And the second aspect of that is by using this data, so using digital mineralogy and geochem data at the same time to sort of help in defining deleterious parameters that can be useful for geotech work later on during production. So it's all sort of coming together, and what I like to sort of close off this presentation with is the value of ioGAS as sort of a center point of how of how we like to do things in ioGAS. So just give me a sec. Oops. So really, what is our takeaway? Just to wrap up my talk, is as part of the IMDEX ecosystem of solutions. So basically, by connecting to IMDEX Hub IQ, we are looking at a single source of truth for everything. So ioGAS grabs data that we know have been QA/QC to be spatially accurate. So that's a location aspect of it. And then our structural IQ solutions give insight to the 3D orientation of the rocks that you're looking at in real time for the technical experts to assess. And the Osiris solution allows you to provide real-time digital mineralogy interpretation from spectral data that you can integrate in real time. And lastly, the in-field geoanalysis solutions, it brings it all home by delivering high-quality geochem data from the field straight to our technical experts, such as yourself, geologists, who are sitting in front of your computers. And so all of this allows you to get better value out of the data you collect, and that brings the point across of doing this all in a cost-effective way through the use of the data we collect from our sensors, and it allows you to get to the point much quicker. So that allows you to make timely decision making at the right time, at the right place. So all of this really contributes to an increase in time savings in the data collection process, and the cost savings from optimizing interpretation of data closer to the upstream brings value to the way that you look at your data. So I like to wrap this up just by saying that ioGAS creates value in our IMDEX ecosystem by allowing technical experts such as geologists to quickly make decisions in a data-rich environment. So I'd just like to close this up by saying thank you, and stay tuned for information on our upcoming GasBack webinar, which we're planning to organize soon. And so keep in touch via LinkedIn. You can add me on LinkedIn if you want. And if you want to ask me any questions about ioGAS, please do so. And you can find more info on our website, on our social media page up on LinkedIn. So thank you so much, and have a good day.
All right, thank you, Putra. We haven't received any questions yet, so if you've got any questions to any of the presenters, please feel free to post them in the question section, and we'll get them answered. There is a question from Stephanie asking, do you plan to add a geochronology feature into ioGAS in the future? I think, Putra, that would be a question to you.
Yep. So geochronology plots, we actually have that as part of our feature things in our pipeline. We're not sure how we're going to implement that just yet, but it is in our system to look at. But if you'd like to know more about it, or if you want to send us more info, just shoot me an email, or you can contact us via our website.
All right, thanks, Putra. We got a question pretty much to everyone. Is this recording will be available for the from this presentation? Would be, yeah, I think we will be able to share this. Everyone happy to share it?
Yep, I think it's good.
Cool. Yep, we will be able to share it, Ria. Anyone else? Any questions?
I think I can break the silence a little bit, and I guess just thanks for everyone who's spent the time today and listened to what we talk. And as Putra and Sasha and myself, you know, if there are further questions, please reach out to either us directly or any of the team in IMDEX that may be able to talk through it. I think we're all, you know, really passionate about each and every one of these topics, and you know, would like to, you know, maybe expand on it a little bit more that may be more relevant to some of these use cases. So.
Thanks, Charles. We got Natalie is asking, is the same handheld device used for XRD and XRF?
Sasha, would you like to take that
Maybe.
question?
Okay, yeah. No, I don't think they're quite different. So the XRF is its own sort of handheld, such as the Vanta, and XRD I don't think is a handheld yet. It's like a benchtop, and they have a field portable benchtop XRD, and then you have the infrared, which is the TerraSpec or the Halo or the Trek. So yeah, they're each their own instrument. Not combined yet. Yeah, one day maybe we might have one that does everything, which would be awesome.
Yeah.
Thank you, Sasha. There's another question from Stephanie asking, why is NIR not used as widely in exploration academia yet, despite its advantages, especially when used with PXRF?
Yeah, excellent question. I think up till recently, really, we haven't had an easy way of interpreting the spectra. So people have been expected to have in-house spectral experts. And this is the main reason why we made the series, is so that we can actually provide the data, the mineral information to the geologists, so that you can start doing what you do best, really, just focus on the geology rather than trying to be a spectral expert to work with the data. Yeah. No, excellent question. But it's coming. You know, I think we're seeing a resurgence really in interest, and people are finding it more easy as the series gets more out there.
Thank you, Sasha.
That's it.
Yeah. Can't see any more questions. So maybe we can just close up this session. And if you've got any further questions, we will be sending out a webinar recording. And yeah, if you've got any questions, feel free to reply back to the email, and yeah, we will get them answered. But yeah, thank you everyone for joining this session, and thank you for all three presenters for your very informative presentation, and yeah, we really enjoy it.
Thank you. Thanks.
Thanks all.
Bye. Thanks. Bye, everybody. Thank you.
Have a good
Bye.
day.
Bye.